All right. Just FYI, the key to problem set 2 is available on Learning Suite if you want to compare your answers with anything that was marked wrong. You can also compare answers for things that weren't graded by the TAs to see whether you got those right. There's also an alternative problem set 2 that you can look at if you need to submit corrections. I have some test corrections forms here. Nope, I had them. No, they're out there somewhere. There's some correction forms here if you want to submit corrections to problem set 2. And as I said, there's a key available for the problem set 1 corrections as well. Okay. So we have been talking about carbonyl reactivity. By considering the leaving group, we have assessed the efficiency of this elimination step versus the protonation step. Good leaving groups will tend to leave, and not good leaving groups will tend to not leave. And we put them in order. We have seen that chloride and carboxylate, phosphate, thiolate are pretty good leaving groups. I would call the negatively charged oxygen okay, but not great. Effectively, if you look at that elimination reaction, did I press record? Yes. If you look at that elimination reaction, the thing that leaves, if you want it to leave, the thing that leaves should be as reactive or less than a negatively charged oxygen. The negatively charged oxygen here, which I'm going to highlight in, I guess, blue, is the kicker offer. And so generally, leaving groups that are more stable than the kicker offer are okay getting kicked off. So if your leaving group is a negatively charged oxygen or more reactive, or if your leaving group is a negatively charged oxygen or an even better leaving group than an alkoxide, then this elimination step is generally okay. So I would put this sort of as the dividing line. These can all be removed by a negatively charged kicker offer. Okay? In other words, it is reasonable to have alkoxides, thiolates, phosphates, carboxylates, and chlorides leave if your tetrahedral intermediate has this negatively charged oxygen. In contrast, if your tetrahedral intermediate has a leaving group that's worse or more reactive, sorry, I'm screwing this up. If you have a leaving group that is a worse leaving group than a negatively charged oxygen, then these generally don't leave. Okay, so that means that you would expect acyl chlorides, anhydrides, phosphates, thioesters, and esters to all do that elimination step, but you wouldn't expect aldehydes, amides, or ketones to do the elimination step. Amides could do the elimination step if you protonated the leaving group first, and we'll see that biology tends to do that. Now, as I said before the break, the second thing we want to consider is the addition step. That is nucleophilic attack. And the real question is, how electron poor is the carbonyl carbon? Essentially, we're going to be asking to look at this molecule and to consider this resonance structure where the pi electrons from the carbon-oxygen pi bond go out onto the carbonyl carbon, and the go out onto the carbonyl oxygen, and the carbonyl carbon is left with a positive charge. And we're going to ask the question, how does the Y group influence the electron density on the carbonyl carbon? What do I mean by that? There's a lot of ways to consider that, but the best one is to note that, and I'm not even saying what the Y group is, but some Y groups have lone pair electrons on them, and those lone pair electrons can donate into the carbonyl carbon to create this resonance structure where there'd be a positive charge on the Y group instead of on the carbonyl carbon. This process is called electron donation by resonance. What do you think about that? Would you expect a resonance electron donation by the Y group to make the carbonyl carbon more or less electron poor? What should that do to that positive charge on the carbonyl carbon? Tends to spread it out, get rid of it, right? So, better Y groups that are better electron donors make the carbonyl carbon less electron poor, and therefore they make the corresponding carbonyl compound less electrophilic. Okay? So in assessing how likely nucleophilic attack is to occur, because the nucleophile attacks at the carbonyl carbon, Y groups that spread out or decrease the positive charge on the carbonyl carbon are going to make the molecule less electrophilic. That means less reactive to the addition step. So now we want to look at these same compounds that we've looked at before, and we want to ask, are they potential electron donors? All right? So let's redraw some of these molecules. We'll draw them in order of leaving groupability. Go ahead.
Does the carbon up above have a positive charge or a negative charge?
The oxygen above has a negative charge. The carbonyl carbon has a positive charge.
But isn't it only connected to 3 things?
Yes, there's no lone pair on that carbon. If there were a lone pair on a carbon that was only bonded to 3 things, that carbon would have a positive charge. I'm sorry, why do I do that? If a carbon were bonded to only 3 things and had a lone pair, it should have a negative formal charge. If it's bonded to 3 things without a lone pair, it's going to have a positive charge. You got it? Got it now? Okay, good. All right, so let's write these compounds in order of leaving groupability, and let's see what we think about electron donating ability. So the first question we want to ask is, okay, does that thing have lone pairs? All right, so if it has lone pairs, then it can be an electron donor. And EDG stands for electron donating group. If it does, then you want to ask the second question, how good? And in general, lone pairs on electron donating groups are more reactive for conjugate bases of weaker acids. That is, if the more reactive that the Y group is as a base, the better it is as an electron donating group. So we could actually start this comparison between the acid chloride and the anhydride. Both of them have lone pairs. Which is the better donating group? And to do that, draw the leaving group after it has left, and then consider how reactive that leaving group is. To do that, you can draw the conjugate acid of the leaving group and write down its pKa. What we're doing here is essentially the same thing as we did during the first half of the class. HCl has a pKa of -7. The carboxylate has a pKa of 4. Chloride is the less reactive base. Carboxylate is the more reactive base. So who's a better donor? Okay, you got it backwards, so we need to fix the process. A good electron donating group has reactive lone pairs. Good electron donating groups are therefore conjugate bases of weak acids. The weaker the acid, the more reactive the conjugate base. So, Cl- is less reactive than carboxylate. That means carboxylate is a better electron donating group. Okay? You follow that conclusion? There are questions about that? Chloride is the worse electron donating group. And correspondingly then, which one should be most reactive in that nucleophilic addition step? Which one has the biggest positive charge on the carbonyl carbon? One with a chloride, right? Most reactive to nucleophilic addition. And then this one would be less relative, okay? Yes?
Can you explain again why the carboxylic acid is better?
Yep. The carboxylic acid is a better, the carboxylate as a Y group is a better electron donating group than chloride, because it's more willing to share its electrons. You can tell its willingness to share its electrons by asking how stable the leaving group is on its own. Chloride, to compare how stable the leaving groups are on their own, you look at the acidity of their conjugate acids. HCl is much more acidic than acetic acid, than the carboxylic acid. The reason for that is its conjugate base is so much more stable. One definition of a stable conjugate base is its lone pairs are really low in energy. Real low energy lone pairs are less likely to donate by resonance. And what we talked about, resonance donation is important because it spreads out the positive charge on the carbonyl. So this is kind of convoluted, right? Chloride's really low in energy. Its lone pairs don't like to donate electron density by resonance. That means there's more positive charge on the carbonyl carbon, which means it's more reactive towards a nucleophile. Yeah?
So for leading groups, for the best leading groups, we're looking for the ones that have like the strongest acid. But for the electron donating groups, we're looking for the one that has the weakest acid.
Right. For good leaving groups, you're looking for the one that has the strongest conjugate acid. For best donating groups, you're looking for the one that has the weakest conjugate acid. Yeah?
Does the reactivity as an electrophile always correspond with the leaving group?
Great question, and we're getting there. So the answer is, for the most part, unless you get an answer to no to this question, does it have a lone pair? So we could follow along with our list from above, where we did chlorides more reactive to addition than anhydrides, which are more reactive to addition than our acyl phosphates. Again, simply ranked by the ability of the leaving group to be an electron donor. Better leaving group, worse electron donor. And that would be true for the thioesters as well, and that would also be true for the esters. Notice that all of these pass the first question, does it have lone pairs on the leaving group? What happens when you get to the aldehyde? H minus is a cruddy leaving group, but this is not an electron donating group. Why? Because it has no lone pairs on H. Right? So that means that for the aldehyde, the positively charged, the carbonyl carbon is very electron poor. It has no mitigating electron donating group to spread out the positive charge. So even though H minus is a cruddy leaving group, and even though aldehydes don't do the elimination step, aldehydes are very, very reactive to the nucleophilic addition step. Okay? This is subtle, and that's why we're talking about it. You would have, if you all you know is leaving group ability, you've been like, oh, aldehydes are just so unreactive. False. It's true that they don't do elimination steps because H minus is a cruddy leaving group, but the hydrogen has no lone pairs. It's not an electron donor, so the aldehyde carbon is very electron poor. So in terms of nucleophilic addition, aldehydes are just as reactive as acid chlorides and hydrides, thioesters, etc. Okay? Same thing for ketones. If you go to the ketone, where the R group is, where the Y group is a methyl group, again, CH3 minus is a very cruddy leaving group, but there are no lone pairs, so it is not an electron donating group, and therefore the aldehyde or the ketone experiences, again, the full positive charge on the carbonyl carbon. The ketone carbonyl carbon is very electron poor. Okay? Last, I think, on our list is what I'm going to do, because aldehydes and ketones are different, is I'm going to just drag them down here. And just make the note, aldehydes and ketones are different. Going back to the amide, it is clear that the amide has a better electron donating group than the ester. Why is that? Couple of ways you could come to that conclusion. Why is this a better electron donor than this? Oxygen's more electronegative, it's less likely to share its electrons by donation. So yeah, nitrogen is less electronegative than oxygen and less likely to share. What we're saying is that amides have the best electron donating group, so they are least reactive to nucleophilic attack. Esters are more reactive to nucleophilic attack. Thioesters are even more reactive, and so on. Okay? So, for the elimination step, follow leaving group ability. For the nucleophilic addition step, follow leaving group ability, sort of, but you got to ask, does it have a lone pair? The ketone and the aldehyde don't on the Y group, and therefore they're very reactive. Okay? Now, we're almost to the point where we're going to start doing reactions. nature can work with cruddy leaving groups and excellent electron donors. And they will do this using something that we call acid-base catalysis. So consider this amide. It is the least reactive on our list to nucleophilic addition. So we would conclude that it would be difficult for a nucleophile to attack the carbonyl carbon. So what nature will often do is to protonate the carbonyl oxygen first. That forces the carbonyl oxygen to feel a full positive charge. So imagine, what is the HOMO of an amide? It's lone pairs on the oxygen. Electrons attack the proton of an acid. We get to this protonated carbonyl that's called an oxonium ion. And that oxonium ion has a resonance structure in which there's a full positive charge on the carbonyl carbon. Whereas before, there was only a partial positive charge on the carbonyl carbon. That makes it much easier for a nucleophile to attack. So we will see some reactions where if we protonate a carbonyl compound first, then we can start to do chemistry, but not before. All right. All of this now, and we've sort of done question 2 on your quiz, though I haven't given you time to work on it. Of the molecules that are on your quiz, if you had to put number 1 in terms of donating group, what would it be? Okay, trick question. Remember, the first question you ask is, when it's in a carbonyl compound, does it have lone pairs? If it doesn't, it's not a donating group. So we can exclude CH3 minus and H minus because they lack lone pairs that allow them to be resonance donors. Of the rest of them, which is the best? Yeah, the RNH minus, we'll put that as 1. That's the best donating group, electron donating group. Who's next? The alkoxide, then thioester, then phosphate, then carboxylate, then chloride. Okay? So, again, yeah, go ahead.
Just like the question's asking increasing electron donating.
Oh, okay, increasing electron donating ability. So now we got to go and erase everything. Always read the question. 6, 5, help, 4, 3, 2, 1. Best, worst. Okay, good. Now, with this in mind, we've got a pretty good picture of reactivity of carbonyl compounds. And though we have learned to rank them today in terms of reactivity, we're going to divide them into 4 simple groups. Okay? Biological groupings of reactive carbonyl compounds from most electrophilic to least. And what we're doing is informed by what we've just discussed about the efficiency of the nucleophilic addition step and the efficiency of the elimination step. Combining what we know about electron donating groups and leaving groups, and about nucleophilic addition versus the elimination step. Okay, so level 1, most reactive. In no particular order, we're going to include, and I'm going to include on this list, we could include the anhydrides and the acid chlorides, but they're not found very often in biology. We're going to include aldehydes, ketones, thioesters, and acyl phosphates. This is going to be our first set of most reactive carbonyl compounds. Just going to group them together, and if you notice, these ones have no electron donating group, the aldehydes and the ketones, and these have electron donating groups / Y groups with conjugate acids whose pKa's are sort of less than 16. Level 2, pretty simple, is only esters. Level 3, also pretty simple, only amides. Okay. Now level 4 is something that you may have noticed is strangely absent from our list. We could write it like this, and that is a carboxylic acid, and we could talk about what the leaving group is, but we don't even need to. What is the pKa of this proton? It's about 4. At physiological pH, what is the predominant form of a carboxylic acid? If pH is 7, then, and pKa for the carboxylic acid is 4, that means at pH 7 that proton is gone. The carboxylate form dominates at pH 7.4. Now, is something with a negative charge already on it a leaving group? Can't leave. It would leave as O2 minus, which would be ridiculous, right? But because of its negative charge, it is an excellent electron donating group, meaning that the carbonyl carbon of a carboxylate is not very electron poor, meaning the carboxylate is not an electrophile. Makes sense, right? It's already negatively charged. Okay, so this is our order, our ranking of biological molecules in order of reactivity, most reactive to least reactive. And this is really important because it will help you understand why reactions happen. Some reactions are downhill in energy, meaning they're very efficient and they happen quickly, and the products are more stable than the starting materials. Other reactions are uphill in energy, and then others are more neutral. A reaction that takes a level 1 carbonyl and converts it to a level 2, that's downhill. You'd expect that to be downhill in energy, very favorable. A reaction that takes a level 4 compound and converts it into a level 1, you would predict that to be very uphill, and likely it would require some other reaction to pay for it. Yeah?
In the quiz, didn't we say that carboxylate was worse at electron donating and better at reactive?
we said that the carboxylate was a better donor than the chloride. But down here, the carboxylate, look at the structure. Remember, the thing we're comparing to is this. So you're drawing from a comparison where we were looking at the carboxylate as a potential leaving group. Here, and we were always focused on the identity of the carbonyl carbon and how electron poor it is. Here, the leaving group, if you look at the carboxylate and ask, is it an electrophile? The Y group is already a negatively charged oxygen, and if it left and took these electrons with it, it would have 2 negative charges. So now we're not thinking about the carboxylate as a leaving group, we're thinking about it, is it even an electrophile? And the answer is no. It's an excellent leaving group, terrible electrophile. You're never going to attack a carboxylate on the carbonyl carbon. Yep. Okay, yes, go ahead.
Also on the quiz, there is one where it's like the oxygen double bond with bond with chloride for the carbonyl carbon. Where would that one fit in like the levels?
Okay, so yeah, on the quiz, I would have included level 1, and we can include acid chlorides here, and also the anhydrides where the carboxylate is the leaving group. The reason I didn't is because these are molecules we use in the lab, but we don't use them in biology. It turns out they're too reactive in biology. If you have these in you, they would kill you. So biology backs off a little bit on the electrophilicity to prevent bad things from happening. Okay. Others? All right, so we're not done yet because we focused today on carbonyl reactivity. And if you can have in your mind these 4 levels of carbonyls, you're going to be pretty well prepared for what's coming. However, biology uses phosphate groups in a very similar way to how it uses carbonyl groups. You've seen phosphate as a leaving group, but now we're going to talk about phosphate as an electrophile. In other words, we're going to put the phosphate in the place of the carbonyl carbon. Let me show you how this works, and we'll develop similar analogies with phosphate groups as we've had for these carbonyl compounds. All right, so what I'm going to do is we're going to call this phosphates as carbonyl analogs. So here is a carboxylic acid. And here is its conjugate base, which is a carboxylate, right? Here is phosphoric acid. Look at what phosphoric acid has in common with carboxylic acid. They both have an oxygen that's doubly bonded to an atom. Okay? Even though this is a phosphorus and this is a carbon, that phosphorus oxygen sigma and pi bond look kind of like a carbonyl if you relax your eyes a little bit. So the phosphorus oxygen sigma and pi bond are a phosphoryl group in the same way that the carbon and oxygen sigma and pi bond are a carbonyl group. Okay? The carboxylic acid has a proton that's acidic, and its pKa is around 4 to go from the carboxylic acid to the monoanion carboxylate. Of course, it's a monoanion, that's all you can do. The phosphoric acid has 3 identical protons. The first one to come off has a pKa of 2-ish, and its conjugate base looks like this. Can you see the analogy to the carboxylate? You still have a carbonyl oxygen and a carbonyl carbon. You still have a phosphoryl oxygen and a phosphorus. And then in the conjugate base, you have this negatively charged oxygen left. And this is called the monoanion. You call it the phosphate group. Okay? Now, unlike the carboxylate, the monoanion phosphate has another proton that has a pKa of 7.2, as we've learned. So that's a difference between between a carboxylate and a phosphate. A carboxylate only has one form. A phosphate has a dianion, and then it has a trianion, and the last proton in the phosphate has a pKa of around 12. Okay, that's for losing that proton. So at pH 7.4, you expect phosphates to be either monoanion or dianion, and you could draw either one and that would be fine. Because at a pH of 7.4, you're really, really close to the pKa, which would mean basically a 50-50 mixture of these two. Similarly, at pH 7.4, you expect carboxylates to be in their negatively charged form rather than the carboxylic acid. See the analogy? Phosphates, carboxylates, very similar. In some ways, you know this already, right? We just did this business of carboxylate as a leaving group, phosphate as a leaving group. Okay? So we're going to put on level 4, we're going to also put the phosphate group. And I'll draw it in one of its appropriate forms at pH 7.2. That would be this monoanion. Okay? Phosphate is a very good leaving group. It is not an electrophile. Okay? For the same reason, for the exact same reasons, the negatively charged oxygen on the phosphate is not a leaving group. It is an excellent electron donor. It makes the carbonyl carbon or the phosphorus, the phosphoryl phosphorus, very electron rich rather than electron poor. Okay? So that's phosphate. Now, let me introduce to you a functional group called the phosphoester. And we're going to compare this to a carbonyl ester. I'll just call it a carboxylic ester, even though that's redundant. There are no other kinds of just plain old esters. This is a carboxylic ester. You have the carbonyl carbon, the carbonyl oxygen, and then you have the OR leaving group. If it left, it would leave as OR minus, and its conjugate acid would be the alcohol with a pKa of 16. Similarly, here is a phosphoester. Based on the pKa's, I'm going to draw it in its monoanionic form. Oops. Here is the leaving group. Here is the phosphoryl phosphorus and the phosphoryl oxygen. Same leaving group in both cases, right? And they have similar stability and reactivity. Okay? So a carboxylic ester and a phosphoester are about in the same level, and that was level 2, right? So on level 2, we're going to include not only esters, but also phosphoesters. Oops. So that would be a phosphate group and an R group. About the same level. Now, are there questions so far about how we're doing this? All right, now let's talk about, are there any level 1 phosphate containing compounds? The answer is yes. Now let's look at the kinds of things that are level 1. You need something that's a good leaving group attached to the carbonyl carbon. We already have an acyl phosphate on the list, so let's start with that one. Level 1 phosphoryl compounds. So you've already seen an acyl phosphate, but you viewed it from this perspective. Previously, you viewed this from this perspective that this is the electrophilic atom, and this is the leaving group. And a nucleophile in purple can attack the carbonyl carbon to give you a tetrahedral intermediate. Also possible, because you know that carboxylates are good leaving groups, is to view this molecule from the following perspective. Let's make the phosphorus the electron poor atom. This is the phosphoryl oxygen, and this is the leaving group. Then, if you had a nucleophile, it could attack at the phosphorus, attacking the phosphorus oxygen pi bond, making pi star, breaking the phosphorus oxygen pi bond, making a new nucleophile phosphate bond. And maybe the carboxylate is the leaving group. So the conclusion is that acyl phosphates are reactive at carbon and at the phosphorus, because either way, you got a good leaving group. We will see both things happen in this class in metabolism. Okay, questions about that? The point is you can use phosphoryl groups like you use carbonyls. And we're going to show you tons of examples of that. Another level, so 2 more level 1 phosphoryl compounds. This is one that forms a lot, or is involved in a lot of biological reactions. This is called a pyrophosphate group. You can see that it looks very much like the acyl phosphate, only now we don't even have a carbonyl carbon anymore. It's phosphates on both sides. And they're identical, so it's actually pointless to try to ask which is more electrophilic. The point is that a nucleophile can attack one of the phosphoryl groups, breaking the carbon-oxygen pi bond, and then in another step, you have a good leaving group, and the good leaving group can leave. What would that look like? Here's what the intermediate would look like after the nucleophile had attacked. Here is the leaving group. Here's the phosphorus that was attacked. Here's the oxygen that got negatively charged. Here's the nucleophile that just added. And here is the substitution reaction where electrons on the negatively charged oxygen kick back down and the leaving group leaves. And you end up with, depending on what your nucleophile is, you end up with a new nucleophile phosphate bond. And over here, you've got the phosphate leaving group. I wanted to show you ATP, but I think that's got to wait for another time. Questions at this stage? Yeah.
So
That's right. So what do you predict for that reaction that we just did? You don't know exactly what the leaving group, what the nucleophile was, but if you go from level 1 to level 4, what do you think? Uphill or downhill? Yeah, you expect this to be way downhill and be very favorable. Okay, that is a lot. We are going to practice that, but if you can get it, everything that follows is going to be so much easier. So we'll pause there. I'm sorry you're taking this during spring. I'm sorry you've got an exam today or tomorrow. Relax, think, and have fun. This is the way. May the force be with you. And was it recorded? Yes.